Looks like we're live. It's 10:30 on a Wednesday. Time to get after this algorithm family stack here. So we'll be talking about some algorithm families today. On the front here, this is just a graph, and we see some nodes and some edges. We see some graph coloring. One thing that's maybe not quite obvious as you look at this right off the bat is no two nodes that are adjacent are the same color. So this is an example of graph coloring here. Looks like there's 10 nodes, 4 red, 3 green, and 3 blue. But nothing adjacent is the same color. And we'll talk about graph coloring in one of our sections later. Our outline for today shows these 6 families of algorithms. So we won't be talking about many algorithms in particular. We're talking about how particular groups of algorithms work together. Our first 2 that kind of run in a pair are brute force and greedy. They've got some relationship to the way that they work. The next pair, divide and conquer and dynamic programming, also have some similarities, and we kind of talk about them and compare and contrast them in these pairs. And lastly, down at the bottom, we've got backtracking and branch and bound, which have some similarities, some very strong relationships as well. So as we start out talking about brute force and greedy algorithms, we'll see how they're related. Both of them are essentially very simple. Brute force algorithms try everything, and the greedy algorithms are only going to take the very best option that they can at any given point. So if there's some planning they could do ahead of time, or looking back to see what's been done in the past, greedy algorithms don't do that. That's too much work for them. They just worry about taking what's best at the time. So our brute force definition is any algorithm that solves a problem in the most simple, direct, or obvious way, hence the name brute force, right? There's no real distinguishable structure or form, meaning that if I say all brute force algorithms have a loop like this, or all brute force algorithms use recursion like this, we don't have that. Every brute force algorithm is sort of an algorithm unto itself. The key is it's just trying everything. Usually pretty easy to implement. That's one of the good things about brute force algorithms. The cons, however, is it does so much work that it often does more work than necessary. May be efficient, but typically it's not, right? So sometimes they're a little bit hard to find as well, just to figure out how to get all of the possible combinations. So those can be some of the things that are working against us with brute force algorithms. Let's take our first brute force example here, and that's counting change. We're going to count change when you go to a store to purchase something. You give them paper money, they give you metal money, or I guess in terms of some other ways we can make changes, they could give them big paper money and they could give you smaller paper money. But that's what the change counting we're talking about. So in the definition, we're talking about the cashier having some collections of coins to return some value, in this case, less than a whole dollar. So various denominations are in the drawer. You've seen this, or possibly you've done it. But the goal is to return however much change is owed to the customer using the smallest number of coins, because more change than they should get angers the store owner, less change than they should get angers the customer, and it's kind of annoying when you get more change more coins than you need. So if I could get 75 cents, I certainly wouldn't want that in 75 pennies. That would satisfy one constraint, which is I get my money back. But it doesn't satisfy the other constraint where we're trying to sort of minimize, that's our objective function, try to minimize the number of coins that are returned, right? This doesn't in the end please the client or the owner, because the owner's constantly got to get more change if we're going through 75 pennies per changing, right? And then the customer walks away with a big old jiggly pocket. Nobody really likes that. So for brute force counting change, let's say that we're going to try all subsets S of the coin, of the coins, right? And the coins are the set of coins is C, and we're trying to make some change that's totaling A. So S and C are sets, A is a value. Since there's n coins in C, there are 2 to the n possible subsets. And how do we get that? Well, we look at each coin as having a 1, 0 option. The coin is either included in this given set of change or it's not included. So that gives me 2 choices for every coin, 2 to the n possible subsets. That's a lot of subsets given any reasonable size n. Once we've taken a look at all 2 to the n of these sets, how do we look at them? Well, the important thing to do is make sure that we've got the right amount of change first. So we have to check first to see if the sum of the subset of the coins equals A. We call this a feasible solution. Every one of the subsets that matches this ends up being my feasible solution sets, right? I'm going to take those, and the amount of time that it takes me to count the money for a given set is on the big O of n, because in the worst case, the set that I could be measuring A for could contain all of the coins. So I have to look through all of the coins in the worst case. In the average case, I maybe only have to look through about half of them, but that's still a big O of n. So I can check to see if the subset equals A, sums to the coin value sums to A. But then I also want to see if I can minimize the size of S, right? So this is my objective function. And what I want to do is pick one of my feasible subsets that has the smallest number of coins in it. So that minimizes S there. And as I do that, what I'm doing is basically I'm using that to count the number of coins. So I can't really do that without looking at every coin in the subset as well, which is, once again, in the worst case, a big O of n, because my subset could contain all of the coins. If you're pretty sharp here, or even if you're not that sharp, you could figure out how in one big O of n loop to both sum up the coins and count the total coins. But it's still n work. So I can say that there's sort of 2 to the n different sets, and I've got to do n work on each one of them. This particular slide is showing some of my options. Now, the coins that we're using are American standard coins, quarter for 25 cents, dime for 10 cents, nickel for 5, and a penny for 1. And what we're trying to do is make 30 cents of change. On this slide, we see a bunch of different rows. It's important to note that these rows are only the rows that sum up to 30. So my brute force is definitely going to look at all of these, but it's also going to look at a lot of other rows. I just can't represent them all on my slide, right? So since there are 2 to the n of them, in this case, we're sort of imagining, like most cashiers do, you imagine like an infinite amount of each coin. You don't really have an infinite amount, but you have more than enough to make a dollar's worth of change. You have more than 4 quarters, you've got more than 10 dimes, you've got more than 5 nickels, or more than 20 nickels, you got more than 100 pennies. That's usually how cash drawers roll. You've got about that much, and you can make any change that you need to. Silence. All right, so I would have a lot more rows, but these are just the rows that have the 30-cent total. And you can see how the number of coins that are included in each one, 0 quarters, 0 dimes, 0 nickels, and 30 pennies. That, of course, equals 30 cents, and it is also 30 coins. So on the farthest column, we'll see how many total coins there are, and each one of the columns underneath a coin tell me how many of that coin there are. We get all the way down to the bottom, we see our optimal way to make 30 cents change with American coins is 1 quarter and 1 nickel. That's 30 cents in 2 coins. So brute force will definitely find this because brute force finds every single combination. Many of them that don't add up to my A, but it checks them all. So brute force is not very sharp, but one thing to point out, and this is an overall discussion of brute force, is brute force always finds the best answer. It always does, because it finds every answer. Many of them that work, many of them that don't, but every single answer that's possible is found with a brute force solution, so therefore we are guaranteed to find the optimal solution no matter what, because brute force would find all of these solutions and more, but definitely that optimal solution is going to be included there. So we talked about the way that this would look. I would have to look at this big O of 2 to the n different sets. And each time I looked at a subset, I would have to do n amount of work to see if it A totaled A and B looked like it had the smallest number of coins in it. So I can say that my best case is a big omega of n times 2 to the n. Worst case is a big O of n times 2 to the n. We're going to be spending n times 2 to the n work. That's just the way that it goes. So best case, we're not going to get any better than n times 2 to the n. But worst case, we're not going to get any worse than n times 2 to the n. So you can imagine this is probably a big theta of n times 2 to the n. All right, that's a little bit on one of our brute force algorithm checks. So next up, we're going to introduce greedy algorithms so we can sort of look at them side by side. So the definition of a greedy algorithm, as I mentioned earlier, is some algorithm that makes a sequence of decisions and never reconsiders anything that it's already done and doesn't ever plan more than the next step ahead as well. So each time it makes a decision, it picks the best possible choice, and we call this the locally optimal decision. So if you're adding things on, you're going to take the biggest possible thing. So one greedy algorithm that you probably have learned is, how do you pack the trunk of the car? Well, you don't want to put a bunch of small stuff in there and then try to put the big suitcase in at the end, and it might not fit. But if you start by putting the biggest item in first and then the next biggest item, that is a greedy algorithm. You put the biggest thing in there, you're most likely to have room for it. And the smaller things can usually fit around the side. But the locally optimal decision when you're doing that is, let me take the largest remaining thing and stick it in the trunk. So we've got some pros here because we have a limited way that we can go at this, right? If I've got one largest item, there's only one thing that I can put into the trunk. So that gives me this pro here that it often runs much faster than brute force because I've got one thing to pick. The cons are that this collection of locally optimal decisions might not end up with a globally optimal solution. And we'll look at some other situations where that happens. So what I mean by that is, if I always take the best that's available at that time, that might not get me the total that I want in the end. And you can think of a situation where, well, if I take a little bit less money right now, I'll make more money in the future. That would be my optimal solution. Well, greedy doesn't do that. Greedy takes as much money as possible at every step. So that's how greedy algorithms work. So as we start to apply that to counting change, we're going to go from the largest to the smallest denomination. As I'm trying to give you change back with a minimal number of coins, the best way to give you change back is in the largest possible coins. So that's what the greedy counting of change does. It says, let me find the largest coin that I can return without overshooting the amount of change that I need to offer, and give that. Once I do that, I can subtract the value of that coin from A, and now that's how much I owe, and I keep doing that. And that is actually how we're taught to make change when we're making change with a change drawer. So if the money is already sorted by value, then it's great. This algorithm ends up being linear because all I have to do is look at every coin and say, well, is this coin too much money? No. Well, since I'm starting from the bigs, if it's not too much money, I'm going to give it to you. Then I'm going to move to the next coin. Is this coin too much money? Well, if it's not, I'm going to give it to you. If it is too much, then I move on to the next coin. So every coin is given that thumbs up or thumbs down choice, but I only have to look at each one of them once. Now, this is also predicated on them being sorted by value, which is why we have change drawers. It's a lot more difficult to make change if I just have a bucket full of coins. I have to pull something out and pull something out and pull something out and say, well, is this the coin I should be giving? So the easy way to do that is to just sort your bucket of coins, and then you can do this in linear time. So this has got a sort of hidden, possibly it has a sort of hidden n log n in it. In some greedy algorithms, you can, in some situations, you can apply a greedy algorithm. You've got some jumbled selection of data, and you say, well, if I just spent n log n time sorting it, I could use a greedy algorithm and get a linear type response, rather than something that would be quadratic by looking at everything in pairs or groups or something like that. So this particular algorithm assumes that they're sorted, and you may be able to make other greedy algorithms apply in certain situations if you sort them. Much like the example that I first gave, which was like, how do I pack the trunk of a car? Well, if I sort the items first, which we don't often do, we just kind of look around and say, well, that's the big one. That's the way humans sort, though. Humans said, that's the biggest suitcase. Well, I've just sorted this whole container, this whole collection of suitcases in less than n log n time because we're human and we can do that. But when we're programming, we do have to get them sorted, so that could be as bad as n log n, right? But once that n log n is done, this particular algorithm finishes up in linear time. So here's the greedy approach to making change. Always pick a quarter if I can. If I still owe you money, I'll try to pick a quarter again. If I can't pick a quarter because it gives you too much money, then I pick a dime. If I can't give you a dime, then I'll give you a nickel. If I can't give you a nickel, then I give you pennies. Really straightforward, and it works. So in this case, you see that using the greedy algorithm for making change, you say, well, I can give a quarter. Now I only owe 5 cents. I can't give a dime. I can give a nickel, and now I owe no 0 cents. And there I've made change in 2 coins. And that was optimal before in brute force, so it's still optimal here in greedy. So we find that now this algorithm looks at 1 row, which is amazing compared to brute force. And we get there pretty quickly. So this leads us to the question, does greedy always work? I've hinted that it doesn't work in all situations, but how about this particular situation? How about just making change? Can you devise a set of coins for which greedy does not yield an optimal solution for some amount? Right? And this slide, I still have to fix it. I apologize. The answer is right there with the question. So, the goal of the question was to give a set of coins and an amount for which an optimal solution isn't gained by using the greedy algorithm. So this particular answer is, what if I give you only pennies, dimes, and quarters, and you need to make 30 cents? Well, the greedy algorithm is going to give a quarter away, then not be able to give any dimes, not have any nickels, and give 5 pennies. And so we end up with 6 coins to make 30 cents. That's what greedy would do. That's not optimal, because if I were to look ahead and say, if I just gave 3 dimes is a lot better than 6 coins, but the greedy algorithm wouldn't find that. So take about 15 seconds here and see if you can't devise another version of this problem yourself. You can change the amount, you can even change the denominations of the coins if you like. But try to think of something where using the greedy algorithm doesn't work. I've proven here that it doesn't always work with just this one example. See if you can come up with your own. And I'm back. All right, so hopefully you came up with one of your own. But you can see here how when I don't have nickels, it eliminates that step 3 there. Step 1 was always pick a quarter if possible. Step 2 was pick dimes if possible. Step 3 was pick nickels if possible. Step 4 is pick pennies if possible. When my drawer is shorted, and sometimes we've all run into the situation where you go to a gas station and they say, hey, we really need ones. And then when it's time for them to give you $7 change, they give you a $5 bill and 8 quarters. Well, that's $7, but it's not my ideal change. But the greedy algorithm doesn't work there because of a gap in the available change. If we didn't have $1 bills, then actually, and that's what's interesting to point out here. In that particular instance, without the existence of a single dollar bill, then my optimal change would be a $5 bill and 8 quarters. But when we know that a $1 bill exists, I can say, well, that's not my ideal change. So this one gives me 6 coins with a quarter and 5 pennies. Here we see that the brute force version would find with these values only these 5 rows. The 30 pennies row, the 1 dime and 20 pennies row. Oh, sorry, that one's right. 1 dime and 20 pennies, 2 dimes and 10 pennies, 3 dimes and no pennies. Those are all 3 different versions of finding it. And the brute force would find something that would be optimal. We see that the optimal value is found there with the 3 dimes row that greedy wouldn't have found. The greedy only found our 1/4 and 5 pennies row. So the greedy only found this bottom row, brute force found these 5 rows, one of which was the optimal solution. So I mentioned earlier that the brute force will always find the optimal solution. Of course, brute force finds many more non-solutions in this, but it also does find that optimal 3-coin solution there. All right, let's talk about a new example. Same 2 families, brute force and greedy. But the problem domain has changed from change to sorting. So the precondition, I've got a random array of integers, and we'll call that my array. And then the post condition is for all I less than n-1, I can say that what's in this array at I is less than or equal to what's in the next position. That's how we think of sorting. We can go into this a bit more in detail, but this covers it. For every position in the array, if I move over 1 to the big side, the thing there has to be not less than what I'm at. It can be bigger or equal to, but it can't be less than. So that's my post condition. That's what I think of as a good sorted container. Let's talk about the brute force approach. The brute force approach is also known as monkey sort. So those of you with a monkey at home, you might want to give this a try. You take a deck of cards, you give it to the monkey throws the cards up in the air, piles them up, looks at them. If they're in the right order, that's sorted. You can imagine there's a lot of different times that the monkey is going to throw these things up in the air before it lands perfectly in order. Even if we never had 2 shots at it coming up the same way for 2 different throws, we were guaranteed that it came up a different way every time the monkey threw it up in the air, we would still take n factorial hits to make sure that we got a sort using brute force. We would just keep throwing them up in the air. Is this your sort? Nope. Is this your sort? Nope. Is this your sort? Nope. So we'd have to do that n factorial times, and in order to make sure that I actually was sorted, I'd have to look through each one of the cards in the stack to make sure that they're in order. So this is a big O of n check to see if I've got it. So man, sorting with monkey sort is inefficient. It's n work, n factorial times. How about sorting with the greedy approach? Let's first find the smallest item and move it to the beginning. That takes me n operations. I have to look through all of the items, find the small one. Next, I'm going to find the next smallest item. Move that one to the second location. Well, now there's 1 fewer card to look at, so that's n-1 operations. And then n-2 operations and ... happens. Lastly, I just leave the largest item in the final location because all the other n-1 items have been put where they belong. Hopefully, that sounds familiar. That's selection sort. Selection sort is a greedy sort. And we know that selection sort works. So this is a particular instance where the greedy approach works. If you look at all of our other elementary sorts, they're actually greedy as well. The insertion sort is a greedy sort. It just says, well, I've got this one thing to insert where it belongs, I'm going to do that. That's the best I can do. I can take this and make my sorted area grow by the very next one. I can make the sorted area grow by the very next one, make the sorted area grow by the very next one. That's greedy. The same with bubble sort. If I just look at these 2 items, all I have to decide is, what's my locally optimal decision? Well, looking at these 2 items, if they're in the wrong order, I'm going to swap them. If they're not in the wrong order, I'm going to leave them. That's a greedy approach. So these are all workable greedy algorithms. Sorting can be done greedily. How about mountain climbing? All right. Those of you that have ever climbed a mountain, I've walked up some hills. I've watched my daughter climb at Planet Rock, and I've even walked up to the top of Stone Mountain in Georgia, just kind of like a really big hill. But haven't really mountain climbed where I'm really trying to get to the top. But That's generally the goal in mountain climbing. And why do you do it? Because it's there. So how does brute force mountain climbing work? Well, if I'm trying to stand on the tallest point of this mountain, a brute force approach would maybe lay out a grid, say 1 by 1 meter squares of the entire mountain footprint. Then the brute force algorithm would stand in each one of those squares. Is this the tallest one? I don't know, but I was there. Is this the tallest one? I don't know, but I was there. After the end of this, if it kept track of the highest possible location, we say, yep, at one point I was at the highest location because I stood everywhere in this mountain footprint. So that's brute force, and you can imagine it's pretty involved. Not a lot of people brute force mountain climb. However, some people do greedy mountain climbing, and the greedy mountain climbing thing is, well, I'm trying to get to the top, so if I can see someplace higher than here, I can take that step and go up. That's a greedy thing to do. What's not a greedy thing to do is say, well, I got to take a step down because I'm trying to get to the top. If I ever take a step down, that is not a very locally optimal decision. I can't make a better decision than going down when I'm trying to get to the top. So in the greedy algorithm, you take any step that will increase your attitude. And if you want to get really greedy, you take the step that most increases your attitude currently, your altitude currently. Increase your own attitude. But take a step that increases altitude. If you keep doing that until you can no longer increase, then hey, you're at the top, right? It kind of depends on where you start. Have you ever seen mountains? Not all of them are just perfectly pyramid, straight up to the top. Some of them have little sub peaks and it goes up a little higher, and so you climb up a little bit, then you got to go down across a ravine and then climb up even higher. So in a greedy algorithm, you would find these local maximum locations. Like, I've got to a place where I can't climb any higher. I'm not at the top. I can see the top, it's over there, but the only way for me to get up there is to go down from here, over, and then up some more. The greedy algorithm wouldn't allow that because it only allows steps that increase our current altitude. So there is an example where a greedy algorithm wouldn't work. How do we prove that a greedy algorithm works or doesn't work? That's this greedy optimality thing that we would like to prove. And if you're going to use or create a new greedy algorithm, you have to come up with this greedy optimality proof. First, we say that the problem needs to have an optimal substructure. And what that means is my optimal solution has to be the combination of some first action and then an optimal solution for what remains after that first action, right? So in the case of making change with a full drawer, if I give you a coin and then use a greedy algorithm on the remaining change, does that work? It does. Then we need this greedy choice property saying that, well, that first choice that first action that I make, can I do that greedily? In the case of making change, you say, well, if I can pick the biggest coin and give you that, and then apply this whole solution again to what remains, if that works, I'm in great shape, right? So in the situation of mountain climbing, it's important to note that if I take one step that raises me up a sub-peak, then the only way that I can get to the optimal solution is to start again at a different location. And I can't apply the mechanism of only taking upward steps to get across this ravine and then up the other side, right? There, it turns out that I don't necessarily have this greedy choice property. I can't pick anything and then go from there to the top, right? There is the optimal substructure in the sense that if I start at the right place and I follow this, I can go there. So I do have part of what I need to make the proof that mountain climbing greedy works, but I don't have enough, right? I have optimal substructure. I can take a first action and then continue taking those actions and get to the top. But only if I start in the right place. And this starting at the right place isn't necessarily something that I can do greedily. I have to do that with a little bit more planning. I say, well, if I start over here, that's not so good. I might have to climb down to a particular location to start at the right place, and I can go straight up. So the greedy optimality principle is that two parts thing. You need an optimal substructure, and you need the greedy choice property. And then we, can apply this. It's applied recursively, though most of the time we are going to program these things iteratively. You can program many greedy algorithms recursively as well, but oftentimes they're just done iteratively. So here's my summary for these two. Brute force solves the problem simply, generates the entire solution set, picks the best, and then always finds the optimal solution, but typically not very efficiently. The greedy algorithms make locally optimal decisions. The best decision I can make now doesn't look back and doesn't plan too far ahead, just takes the best at this moment. It may give an optimal solution, and it's typically better in efficiency than my brute force. But it depends upon this greedy choice property. If I've got this global optimum found by a series of local optimum decisions, I have to have some greedy choice property that says, well, if I start well, no matter how I start, if I start greedily, then I get to the goal. That's my greedy choice property that really makes sure that the greedy algorithms work. So those are the first two families, and we see how they're related. The brute force and greedy are similar because they're both fairly simple. Up next is my subdividing set of families, the divide and conquer algorithms and the dynamic programming algorithms. Hint, DP, staff favorite. All right, so the divide and conquer algorithms and dynamic programming algorithms both divide the problem into some smaller problem and then try to solve that problem. In divide and conquer algorithms, we say that the problem solution is when we can divide this into two or maybe more, depending on the problem, smaller problems, all of which look exactly like the original problem, just smaller, right? Preferably, we can divide this into two equal size problems because that makes my division depth as shallow as, I can generally get it to be. So, of course, if I'm dividing into more than two areas, I would like to get them to be equal size as well. So if I've got this divided into three problems, then I'd like all three of them to be a third of the thing, right? You don't want to say, well, we've got to get rid of this stuff, and here's us three friends, we're going to work on it. I'll take 10% and you two take 45%. It's not a good way to keep friends. It's a nice even division into three sections, but it's not a fair division. So I guess not even division. It's a division into three. But when they're not equal size, you can see how one person may be doing 10% of the work while the other people may be doing 45% of the work, and that's not great. Especially bad if you've got friends where one person does 10% of the work, another person does 10% of the work, and then you do 80% of the work. Nobody likes that. Because then your work is so much larger. Even if you take your problem and divide that into two problems and say, well, I'm going to do half this morning and half in the afternoon, you still have got 40% of the work in the morning and 40% in the afternoon. And so your division goes deeper there. So we often think of these divide and conquer algorithms as recursive because when I make that division, what I've got is a problem that looks exactly like my other problem. And that's how recursion generally works. This looks just like another version of that, which looks like another version of another version of that. So it's often recursive, and this log n, because of the divisions, that says how many subproblems we're going to solve. When we can get these into nice even sections, we end up with something that is logarithmic, right? And depending on how many sections I'm dividing in at each level, that tells me what the base of my logarithm is. So if I'm dividing always into two even sections, I'm going to be log base 2 of n. If I'm dividing into three sections, I'm hopefully going to be log base 3 of n if they're equal sections. But we still know that this is just logarithmic, and so that's what's going on with divide and conquer. And it's also, if you look into the literature, you'll find this as D and Q as opposed to D and C. I'm not sure why that is. It probably has something to do with some other language. But divide and conquer, or D and Q, those are algorithms that are usually pretty efficient. And they have the built-in quote-unquote elegance of recursion. We know that recursive algorithms often look very elegant. They're easily described. You give a base case and then you sort of show the inductive step and it's done. However, not all of our recursive programs are efficient. That's why this quote-unquote elegance of recursion is there. It might be elegant to look at and think about, but still painfully difficult or painfully long to program. So the cons, of course, when I get into recursive programming, I have to get down to base cases. So I've got a small subdomain that I'm like, now that I'm sorting, for instance, when I'm sorting, when I keep dividing and conquering, I got this whole bunch of work to sort. Well, maybe I'll just sort this half, and then maybe I'll sort half of those, and maybe sort half of those. When I get down to the bottom, I've got my base case. So like, how do I sort one item? I don't have to do anything. It's sorted. All right, now I can work my way back up the stack there. So I end up with a lot of calls that have a length of size 0 or 1, or whatever my small subdomains are that my base case are. So the cons of divide and conquer show up there. Sometimes it's also dependent upon initial state of subdomains. So for instance, I can't do a binary search on an unsorted data set. Binary searches work great, but only when my data is sorted. And that is a divide and conquer. Hey, I looked at this thing in the middle. Is it what I'm looking for? No. Well, then the stuff is either over here in this half or in that half. And now I've divided and conquered. And so I can do that, but binary search requires that my data be sorted. Combine and conquer is a close relative of the divide and conquer algorithms. In this case, we start with the smallest subdomain and then combine until we get increasingly larger subdomains until we get all the way up to our size n, right? So in divide and conquer, we start with n things we need to do, and we sort of divide that into n over 2 and n over 4 and n over 8 till we get down to our base case, which is usually 1 or 2 or 0 items, and then we can work our way back up. So we go from big to small. In combine and conquer, we do the opposite thing. We say, well, let's start with the smallest subdomain possible. Let's say I've got n items. I look at this as n sets of size 1, and as I can keep combining them until I get one set of size n. If that sounds familiar, you can find it. So divide and conquer, we think of those as top-down algorithms because you start with the big thing and you go down to small things. In combine and conquer, we think of those as bottom-up. We start with the small things and work our way up. One of the other things that we talked about previously this semester, which was a combine and conquer algorithm, was the way that the merge portion of merge sort works. You start out with these two sets of size 1, and then I combine them into a set of size 2, and I can take two sets of size 2 and combine them into a set of size 4, and two sets of size 4 and combine them, and so on. So there's a combine and conquer algorithm that we've already seen. We talked about binary search as one of our binary search of a sorted list as one of our divide and conquer algorithms. Another one, of course, quick sort. We reviewed that already this semester as well. So we already know some divide and conquer and combine and conquer algorithms. And you can think of others. DP. Dynamic programming algorithms. Now, we're just going to give this a light touch today, dynamic programming. We have an entire lecture devoted to DP. But one of the questions that I get the most in 281 after the midterm exam is, how am I going to do better on the final? I get that all the time. Well, start with DP. There will be a dynamic programming free response question on the exam. That's the way we roll. So we're going to talk about it lightly today. We're going to discuss it again in the future. But if you want to get a head start on it, go learn some DP. Turns out that a lot of DP problems are very similar in structure, and there may be like 8 or 10 very common style DP problems. And once you get those styles down, most DP solutions are some version of one of those. So if you spend some time learning DP and reading a few DP solutions here, 5 or 10 a week between now and the final, I think you're going to do pretty good. All right. Dynamic programming. In DP, what we do is we take and think we got this large problem, I'm going to make it into smaller problems, and every time I solve one of the smaller problems, I'm going to remember that solution. And then later on, if I need to find that solution again, I can go look it up instead of recalculating it. So the definition here says, remember partial solutions when smaller instances are related. And that's where our key difference between DP and D and Q show up. So divide and conquer, we're taking this set, cutting in the middle, and then we're going to work on this half. Later on, maybe we'll work on that half, or in the case of binary search, we'll pick one half to work on. But we don't ever think that something that's over here could also be over here. They're independent. The way that we break this down into smaller subproblems have one of those items in one subproblem or another, but never more than one. Dynamic programming is a special class of problem where I have overlapping subproblems, where I have smaller instances that are related, right? And so in the case of DP, we always end up solving the small instances first. Whether we work ourselves top down or bottom up, doesn't matter. We still solve the small instances first because we need the answer to the small instances to make larger solutions. That's the way that it works. But if I solve these small instances and then store them, I might have to look them up multiple times because my subproblems are related. This one subproblem may use a solution of these three smaller ones, and another subproblem may use the same solution of these three smaller ones. So rather than calculating this 3 for this subproblem and the next subproblem that uses it, I calculate it once, store it, write it down, whatever you want to think of it as. Once I've written it down, later on when another subproblem says, well, I need the answer to those 3 things as well, I don't spend the time calculating, I just look it up, and I get that done in constant time. So this is great because it can take some really inefficient algorithms, something that's like exponential, 2 to the n, and then it can very often turn that into something that is polynomial. And going from exponential to polynomial is amazing. So going from big O of 2 to the n to something like the big O of n to the c, even if that's n squared or n cubed, that's way better than 2 to the n. So that's the great part about DP, and the hard part is the hard part. The con of DP is how hard it is to understand DP. I like to say that it's hard to understand the first 3 times you learn it, because we'll talk about it and you say, oh yeah, I got that. And we'll look at one particular problem, you nod, yeah, that's good, yeah, that's good. And then here's another DP problem, and you go, just deer in the headlights, just staring, I can't figure this out at all. Then you go back and you learn DP again, and you see how DP is applied to that particular problem. Oh yeah, I got that. Now I know DP, I'm ready to go. You see another DP problem that's not at all like you were looking at before, and you do the again. So DP can be kind of a challenge, but once you get it, it's really pretty impressive. So here's my example, this Fibonacci numbers using DP, and we probably wouldn't use DP to solve Fibonacci. There's better ways to do it, but Fibonacci is very easily understood, and it's a great illustration of how this principle works. So here's the Fibonacci number definition, right? I've got these 2 base cases. F of 0 is 0, f of 1 is 1. Then I've got my recursive case. I say that f of n, for any n, is equal to the sum of the 2 smaller numbers before it, f of n minus 1 plus f of n minus 2. So if I've got these 2 base cases, then I can get that for any number. So let's look at f of 50. I say f of 50 is really just the sum of f of 49 and sum of f of 48. Great. There's 2 smaller subproblems. I got no problem pulling it off. But how do I solve f of 49? It's really just f of 48 plus f of 47. F of 48 is f of 47 plus f of 46. And hey, wait. There's an overlap. Look at that. I've got fib 48 calculated once. Then I had to calculate fib of 47 twice. But DP would say, hey, we'll calculate it once and write it down. And the next time somebody asks for fib 47, we'll just go look it up. And I can do that in a constant amount of time rather than what it's going to take me to get this done here, right? Because I keep going down the tree here. We end up with fib 50 is really fib 47 plus fib 46 plus fib 46 plus fib 45 plus fib 46 plus fib 45 plus fib 45 plus fib 44. And if you were listening there, you heard that I hit fib 46 3 times. I hit fib 45 3 times as well. So I'm doing a lot of work in those because I've got a long list of things that show up under this that do not fit on this slide as we get ourselves all the way down to the base case of fib 0 and fib 1 to make my solution to fib 50. And there's going to be a lot of times that I calculate fib of 5 if I don't write it down, which is why if I write the real simple version of Fibonacci, the really elegant version of it that I can write recursively, it ends up very time inefficient. Here's my summary of these two families. I say the divide and conquer divides a problem into non-overlapping subspaces. My subproblems are unrelated. Then we solve within each subspace, and I either combine or maybe I can just take the value from the best of those depending on the algorithm in question. But we say that our divide and conquer algorithms are most efficient when my subspaces divide evenly. Why is that? Because it minimizes the number of calls that I have. So imagine I was dividing and conquering, right? What if you were looking up a word in the dictionary, right? Looking up a word in the dictionary is actually a binary search. We don't think of it as a binary search because we put a little bit of human into it. We say, well, if I'm looking up something that starts with a C, I don't go to the middle of the dictionary. I just kind of estimate where the C's start. That's a modified binary search with some overlaid human ingenuity to it, right? But if I wanted to do a binary search, even when I get into the C's, I say, well, here's where the C's are. Or maybe when I first grab it open, I'm like, well, I was trying to get to the C's, but I got to the D's. Well, I don't look after D, I just look before D. And then I get to the middle of C's, well, is it before this in C's or is this after this in C's? And this really is a binary search, right? So I get my most efficient when I remove the most number of pages with my split, right? So my very inefficient divide and conquer search of a dictionary would be, well, let's look at the first page. I know it's either on this first page or these remaining n-1 page. That's a division, and if I conquer this page, that's divide and conquer. So I end up with a very inefficient search that devolves to what? It devolves to linear. If I say, well, let's look at this page. Nope, not there, conquered. Next page, nope, not there, conquered. If I go through each one of those, that is a divide and conquer, but I am not dividing my subsets equally. If I were to say, well, I'm going to start at the middle of the dictionary and then take the middle of that half and the middle of that half, I'm going to get there really quickly in log n time. So that's why I say D and Q algorithms are most efficient when my subspaces divide evenly. Dynamic programming is similar to divide and conquer because it takes a big problem and makes it into a smaller problem that works just like the bigger problem, but is just smaller. Only works, however, DP only works when I've got overlapping subspaces. I cannot apply a divide and conquer algorithm to subproblems that do not have a relationship. I just waste my time. I solve a problem once, I write it down, and then I never use that solution again. I do all of the same work that I would have done in divide and conquer while getting none of the benefits of dynamic programming. So we only can use this when I've got partial solutions needed later, and oftentimes I'm looking nearby for previously calculated values. If that's not super clear, don't worry. It will be when we talk about DP in its very own lecture coming up in the next couple of days. All right. So there's my my subdividing pair of algorithm families. Both of these take the bigger problem, make it smaller problems, and they work on different kinds of dividable problems. The last pair of algorithm families I'll be talking about both have their own lectures as well. We'll be talking about backtracking and branch and bound in a separate lecture. We'll be doing some of this stuff in our upcoming projects as well, or upcoming project. That's project 4. We look at these two algorithm families in terms of the types of problems that they solve. So we'll start with what's known as a constraint satisfaction problem. And that's one where we say, is there a way that I can put together enough things that don't violate any constraint? So if you've ever played a number puzzle, they're called Latin squares. One of the famous Latin square puzzles is, of course, Sudoku, where in Sudoku you've got to fill this grid that's 9 by 9 with 81 different values, but they're all just copies of 1 through 9, and I have to have unique values of 1 through 9 in each column, no copies, and unique values of 1 through 9 in each row, and then there's also the houses or the boxes that have values of 1 through 9 in them as well. So those are constraints. The constraint that I'm mentioning is I can only have one value each, 1 through 9, in any given column. That is a constraint. So constraint satisfaction problems are some set of constraints, and often we need to know, hey, can I solve this without violating any constraints? Many times there are more than one solution, but depending on the problem, there may be only one. So the way that Sudoku problems work is there's one unique way to solve the puzzle with the given initial state. But other constraint satisfaction problems can get you multiple solutions. Some examples we have of constraint satisfaction problems is sorting. We've already looked at sorting. That's a constraint satisfaction problem. And we saw that constraint when we said, what is the definition of sorting? We said for all I that is less than n minus 1, if what's at I is less than or equal to then what's at I plus 1, I would say that's sorted. That's my constraint. I'm looking at, I never want one value to be in front of something that is smaller than it. That's not a sort. So mazes are constraint satisfaction problems. We haven't talked too much about spanning trees, but a spanning tree is a type of graph that says I've got all of these nodes. Is there a way that I can connect all of the nodes in one tree? That's a spanning tree. The next kind of problem that I look at is an optimization problem. And optimization problems have, by tacit, they've got a constraint satisfaction problem already wrapped up in there, right? Because I can't say, well, how are you going to get this problem solved and then optimize it? You can't optimize a solution that violates a constraint. You can't break the rules and come up with an optimal solution. So we have to have constraint satisfaction as well as minimizing some objective function. So when we were making change, we were saying the constraint satisfaction was I need to give them back the money that they are owed. They owed 30 cents, I need to give them back 30 cents. That was the constraint satisfaction, because if I gave them back less money, they were upset. If I gave them back more money, the boss was upset. Then we've got this optimization step, was applying some objective function that says, well, given the change that we gave them, how many coins were there? I want to minimize that number of coins. So examples here of optimization problems are giving change, MST. We'll also be looking at traveling salesperson problem. So those are some optimization problems. Constraint satisfaction problems, when we're solving them, we can usually stop as soon as we've found a solution. Oftentimes, that's enough. Most times in constraint satisfaction, that's enough. Certainly enough in Sudoku. Once I've filled the board out, I'm done. I don't need to figure out if there's another way to do this. In that particular case, there isn't, but other situations, there might not be one, right? So if my goal was to just make sure that you had your coins, no matter how many coins they were, if you were getting that 30 cents, I give you 30 cents and say, go away, you've got your money. Wait a minute, I got a whole bunch of pennies here. Okay, but I gave you 30 cents, walk away, right? So that's the constraint satisfaction only. We can get one solution and say, hey, I gave you your money, move on. Optimization though, we can't usually stop early. Say, well, here's 30 pennies, is that good? Or is there any way I could do better? Well, I could do better if I took 5 of these pennies away and they give you 25 pennies and a nickel. Well, what if I took 5 more pennies away and now I got 20 pennies and 2 nickels? Well, there's another solution. So I can't stop when I find a solution. I generally have to check almost all of this feasibility set, right? That's all of the possible solutions, right? Because I never know when I might find another solution that's actually better than the best solution I've ever seen. And until I've seen all of those solutions or a way to guarantee that I can't find a better solution, hint, later, then I still have to keep looking, right? So in optimization, I've got to see more, generally have to see more than one solution, because I never know when I've found the best solution until I've seen them all, or I've got a way to rule out any other solutions as being improvements. So now that we've got these two types of problems set up, constraint satisfaction and optimization, I'm going to add this line here that says constraint satisfaction problems can rely on a backtracking algorithm, which means that you can solve it with backtracking. Optimization problems can rely on branch and bound algorithms, which means that an optimization problem can be solved with branch and bound. For any particular problem, there may be a more efficient approach than backtracking or branch and bound, but this is like better than having to do brute force. So rather than having to do brute force and constraint satisfaction, if I can't come up with something super elegant, I can always use backtracking, and that's going to be better than brute force, typically. Same thing with optimization. I could do a brute force, but I could use a branch and bound and find something better, generally. So if there's not a much more efficient approach, I can always fall back on these two. Backtracking algorithms. Now, listen close. As I define this, I say a backtracking algorithm will systematically consider all possible outcomes of each decision, but prune searches that do not satisfy constraints. What does that sound like? Sounds awfully brute force-ish. Force-ish? Brute force-ish. Systematically consider all possible outcomes. That sounds like brute force. And it is. It turns out that backtracking typically has an asymptotic complexity similar to brute force. But, right there in the sentence it says but we prune searches that do not satisfy constraints. And this often helps us out tremendously. So, for instance, if I'm in a death maze, and this death maze has 10 different things that I need to get past without dying. Now, if I take a turn down this death maze that kills me, I don't have to worry about anything after that trip, do I? Because those other 9 puzzles that show up after that are not really important once dead. So I can prune that, and I don't have to worry about making those 9 decisions after this one poor decision. So I am still systematically considering all possible outcomes, because it turns out that every possible outcome after me dying in the first step is me being dead at the end. So I don't have to look at all of them. So I can think of that as considering them without doing the work to go into them. So we use this backtracking to say, well, once I've violated a constraint here, I no longer need to go any farther. So one way to think of backtracking as really is a depth first search. We're trying to get all the way to the solution. We're trying to work our way all the way down this decision tree to the bottom. Once I've made the last decision, I got to the bottom, I have solved the problem. I have done it. But I've got pruning in there. When I make a bad decision and I fail here, I don't need to discover anything below this. Because if this fails up here, going below that is unnecessary. I'm going to backtrack, I'm going to go up and try to go over and work my way down to the bottom again. So you can think of backtracking as depth first search with pruning. The pros are that this actually eliminates an exhaustive search. So here's where we get to real brute force. Exhaustive search is everything. Where this sounded brute force-ish, systematically consider all possible outcomes, it doesn't actually end up exhaustive because we get to prune searches that don't satisfy, and oftentimes, since we're trying to get a solution that satisfies any constraint, then as soon as I finish, I'm done. I don't have to see, well, let me find another version and another version and another version, and I can compare all of these versions and see which one is best. I'm going to take the first one I get and call that a solution. When you're trying to get out of a death maze and you see the other side, you don't go back in and say, well, what if I took that other right turn? Maybe it would have been a little bit shorter. No, you're out. You keep moving. So the search space still looks fairly large, but because we don't have to look at everything, because we can prune things that violate constraints, and because we can take the first possible answer, we end up with something that has the same asymptotic complexity as brute force generally, but is also generally much faster. So it's hard to a lot of times it's hard to verify those because proving that is so much more work. But when you learn how to apply backtracking, then you know that you've done something better than brute force. So our first example here leads us back to our cover slide, which is graph coloring. In this case, we're going to be doing graph coloring in 4 colors. And it was not me who colored those words in multiple colors. That was some other mean slide person just trying to make Dr. P's life hard. All right, so What we're going to do in graph coloring is we're going to assign a color to each vertex. And in the case of graph coloring, we're trying to do this in a way that no two vertices that are connected by an edge, adjacent, no two adjacent vertices have the same color. Some graphs can be four-colored and some can't. So think of how that might work. Is there a way to four-color the graph that I had on the previous page, on the cover slide? Meaning, can I take those 10 points with four colors and make sure that no two points are adjacent with the same color? So the question I often get is, given some graph, is it four-colorable? One place that this often happens is this exact example right here, this map of the United States. Now, I can't say that those are the greatest colors to color a map with, but there's a red there, there's a pretty bright purple, a bright green, and a yellow, and the entire country is colored, every state individually, and if you look closely, there is no state that is touching a state of the same color. Even Alaska and Hawaii, who are off the map here, but they're different colors. So how does this get done? How does the graph get colored this way without coloring adjacent states the same color? Well, we take a map like this, not to be confused with an unordered map, the hash table sort of implementation. We're talking about a real cartographic map. And the way that I do that is I say that a cartographic map can be drawn as a planar graph. And a planar graph is one where I've got all my vertices drawn and all my edges, and none of my edges cross. I've got no lines that intersect. They can meet at a node, but no lines actually cross each other. And any cartographic map that I draw can be converted to a planar map. The way we do this is take each state or each region and turn that into a node, and we take each border and turn that into an edge. So two regions that are connected by a border have an edge between them. So two nodes that represent those two regions have edges between them. Here's an example of the southeastern United States. We've got Tennessee, North Carolina, Mississippi, Alabama, Georgia, South Carolina, and Florida. So this is just a small corner of it. And what we're going to try to do is say, let's look at this map as a graph. And on the right side, we see that we've got a bunch of nodes that have edges between them. Tennessee touches Mississippi. There's an edge from the Tennessee blob to the Mississippi blob. Tennessee touches Alabama. There's an edge from the Tennessee blob to the Alabama blob. Mississippi touches Alabama as well, so there's an edge between them. And that's how we've converted this cartographic map to a planar graph over there, which is just a graph with an additional rule that none of my lines cross. You see that none of those edges actually cross each other. They just meet at the blobs but do not intersect. So using four colors, let's go with something a little bit more calm here. Red, blue, green, and orange. I'm not saying that those are Dr. P approved colors, but they're certainly better than the previous slide. So as I start here, let's start in Mississippi. We're going to work our way sort of clockwise around the map, or at least around the graph, and I'm just going to keep updating my colors. I go from red to blue to green to orange, red to blue to green to orange. So I say Mississippi is red, that's good. I move to Tennessee and color that blue. It's good. I so far have two colors. I can't possibly have two states that are adjacent because I've only got two colors on two states. My third color comes in North Carolina, makes that green. Mississippi touches Tennessee, they're different colors, red and blue. Tennessee touches North Carolina, they're different colors, red and blue. Everything is good. If I go around to South Carolina now, it touches North Carolina, it's orange. Green and orange touching each other, no problem. I keep working my way around clockwise. I end up with Georgia here in the middle. Georgia is adjacent to Tennessee, North Carolina, South Carolina, Florida, and Alabama. The only thing Georgia isn't adjacent to is Mississippi in this region. But since they're not adjacent and they're the same color, I haven't violated any constraints. They're not adjacent in the same color. Everything that Georgia is adjacent to is either blue, green, or orange, and that's okay. Moving clockwise again, I get Florida at blue. It's only adjacent to Georgia and Alabama. Georgia is red, Florida is blue, that's good. Alabama is uncolored, we're still good. I keep moving my way through the color scheme. I'm going to try to put green in there at Alabama, and lo and behold, I have a map coloring that works. Mississippi's red, Tennessee is blue, North Carolina is green, South Carolina is orange, Georgia's red, Florida's blue, Alabama's green, and no borders are between two states of the same color. All right. Let's try this with 3 colors, because it was so easy with 4. When it gets to be fewer colors, then I've got to use the same colors more often, and it gets a little bit more difficult. We're going to see how we might have to backtrack to get to a solution here. So I'll start out with Mississippi as red, and Tennessee as blue, and North Carolina as green, just as before. They're all the same. They all have the same colors as they did before, and they have the same borders. Now when I go to South Carolina, though, I don't have orange, so I'm just going to reuse red. Red is fine there. North Carolina, South Carolina adjacent, different colors, no problem. When I go to color Georgia, however, Georgia, remember, is adjacent to all of these things. So if I try to put Georgia in there as green, it's adjacent to North Carolina. That doesn't work, right? Sorry. When I try to put Georgia in there as green, it goes back and says, well, I can't color Georgia green. It's adjacent to North Carolina that's green. Okay, well, how about if I try to color Georgia blue? Well, I can't color Georgia blue because it's adjacent to Tennessee, and that's already blue, so that's a violated constraint. What if I color Georgia red? Well, it's adjacent to Carolina, and that's red, or South Carolina, and that's red already as well, so I can't color Georgia any one of these colors without violating a constraint, so let's backtrack. It turns out that this decision for South Carolina being red led me to a place where no available decisions for Georgia were legal. So if I back up and say, well, let's make South Carolina some other color, and I just work my way through the progression, red, blue, green, red, blue, green, red, blue, green, red didn't work, let's make South Carolina blue. Okay, now South Carolina, North Carolina adjacent, different colors, green and blue, no problem. When it comes time for me to place Georgia, I can make Georgia red, no problem. Georgia's now adjacent to Tennessee, Carolina, and South Carolina, and they're all good. All right. How about Florida? I can make Florida blue. That works. I go back through my progression again and color Alabama green, and now I have come up with a 3 coloring of this same region. Now, if you want to try this with a 2 coloring, I'm pretty sure it won't work. But you can try it, and you will have to backtrack along the way as you make a choice, and then you put in another color, and then you say, well, this violates a constraint. Let me go back and try coloring that one another color. And so when we run out of the ability to backtrack, then we find that there's no way to solve this problem given the current set of constraints. So this is the graph coloring. Let's look at how we went from enumeration to backtracking. So enumeration, I take each vertex, let's say vertex v sub 1, and I can consider 4 branches for it, because when I'm 4 coloring, I can say, well, this vertex could be red, green, blue, or orange. All right? So after I've done that, then I take vertex 2 and consider 4 branches there, because each vertex can be of any one of those 4 colors. Then I go on to vertex 3 and consider 4 branches, and I end up with this decision tree that starts up high, goes down for 4, and each one of those sub-decisions gives me 4 more sub-decisions after I've worked my way to the next thing. So when I end up with my violation, my constraint violation is if there's an edge between v sub 1 and v sub 2, if 2 vertices are adjacent, then among those 4 colors for v1 and 4 colors for v2, there's 16 different combinations, I know that 4 of them are dead ends. Red and red, green and green, blue and blue, orange and orange. All the other combinations, red, blue, green, orange, red, green, those are good. There's 12 good versions, but there's 4 bad versions. So I can say that I can prune right away. So for instance, if I've made the decisions for the first color for v1, then I made the decisions for v2, I can say that there's 4 ways that I don't have to continue making decisions, right? Because if v1 and v2 are adjacent and they're the same color, I've already violated any constraint. I don't have to worry about coloring any of the rest of the vertices because v1 and v2 are a constraint violation. All right, backtracking is going to branch on every possibility, and we end up maintaining one or more partial solutions. And it might not be easy to see how this is done. Very often this backtracking partial solution is maintained in a recursive call stack, right? I've got a partial solution and I've tried to extend the solution. I work my way, deeper into the call stack, but when I fail, I work my way back up the call stack, and then I'm like, oh, okay, I've got a partial solution where things weren't so bad before, and I can try to extend that again. Every time I'm trying to extend this solution, I say, well, I've got this partial solution. Let's see if I can extend it. If I don't violate any constraints, then I extend the solution. If I do violate a constraint, then I backtrack. I go back to a previous decision and make another decision there. If I've made all of the different options at a previous decision level, then maybe I go back 2 levels or 3 levels. There's no end to how far you may backtrack when you're trying to get a solution there. You can try everything. That's when we get to the solution there. As I mentioned, it does have the possibility of trying everything, but generally we drop a lot more because we get to do this pruning. And here's a pseudocode version of this M coloring algorithm. So my input is the number of nodes and the number of colors that I have. N is my number of nodes, M is my number of colors, and then I've got this adjacency matrix, W, which has all of my adjacencies that tells me which of my N nodes are next to each other. So if W at IJ is true, then there's an edge between node I and node J. It's false if there's no connection. So the output of this algorithm is going to be all possible colorings. So this is going to be one where we solve the constraint, and because of the structure of the algorithm, it actually solves every possible way to get there. So we said that constraint satisfaction problems can often be quit. We can quit solving it once we've got one particular solution. This particular solution, this algorithm goes through all of the solutions. Here it is. It's not very big, but it's powerful. So I've got this algorithm M coloring here. That's what's declared here at the top, the name of the function. And then the very last line is another call to M coloring. Recursion alert. So this is the recursive function. I've got to have a base case, and I see that right here in these first 3 lines inside the function. If I is equal to n, print vcolor 0 through vcolor n minus 1 and return. There is my base case. This is going to get me out of this recursive function before I recurse. That's key. You can't have a recursive function without a base case, a way to get out. Now, once we are still trying to extend our solution, that's what this loop is going to be doing. So in our backtracking solutions, there is going to be some recursion, which is where we extend the solution, and some iteration, which makes it even harder to understand. Recursive functions are hard enough to understand on their own, but our backtrackings have some loop that has the recursion inside of it. All right, so what I'm trying to do is color each one of my nodes. So this for loop says for each one of the colors, 0 through M, try to color the current node, vcolor at I, that color. So I set vcolor at I equal to that color, and then I've got this if promising check. That if promising check is where I check to see if I've violated any constraints, because this loop says, okay, I'll try every color. As you want Mississippi red, you want Mississippi green, you want Mississippi blue, you want Mississippi orange. That's what this loop is good at. But we don't want to do it if it violates a constraint here, and that's what this if promising does. If it's promising, it means we haven't violated any constraint. Then let's move forward. We called M coloring at the beginning with I equal to some 0, our first decision. And then M coloring here is always taking the next decision by saying I've tried to extend the solution by saying if I called it with I, now I'm going to try calling it with I plus 1. I'm trying to go deeper into the decision tree. Here is promising for this application. Remember, we've got this graph, and I want to say if any 2 adjacent nodes are the same color, then I've violated a constraint, which means this is not a promising solution, right? I've got a sub-solution to this, a solution to a sub-problem here, and I want to keep extending that solution. But as soon as I violate a constraint, there's no way for me to extend that any farther because it's going to be always having violated one constraint. So this promising function returns a Boolean, which is just true or false. It's like, hey, you've just made a new partial solution. Is it going to be part of a full solution? Because if it violates a constraint, it won't be part of a final solution. So if it says it's not promising, there's no need to try to extend the solution past it. All right? So in this case, all it does is just runs through some given index I and looks at all of the other indices j from 0 up to, but not including I, and says, well, if v color at I is equal to v color at j, and there's a true in the adjacency matrix, meaning that they are next to each other. So if v color at I is the same color as v color at j, and I and j are next to each other, this is not promising, return false. Otherwise, return true because we haven't violated any constraints. So that's how backtracking works. When is backtracking efficient? Well, backtracking avoids looking at large portions of the search space because of this pruning. Doesn't necessarily improve the asymptotic complexity because no matter how large that is, if I look at something that's pruning out 99% of the search space, that sounds great. But 0.01 times b to the n is what? It's still big O b to the n. So if we've got this exponential thing, it's still going to look exponential. That's the big O, though. That's the worst it could be. So often it ends up better than that, but asymptotically it does not end up better. Because when I've got a lot of constraints, then it's easy for me to violate a constraint. And a violated constraint is a tree section pruned. There's a part of the decision tree that I no longer have to investigate because a highly constrained problem comes up with constraint violations all the time and cuts out bunches of bunches of the decision tree that we don't have to look at. On the other hand, an under constraint problem, a problem with not a lot of constraints, it just goes down to the bottom really quickly. Decision, 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 no problems, we're done. So when we've got a highly constrained problem or a very lightly constrained problem, backtracking is really efficient because we get to a decision quickly or we prune a lot of the bad decisions really easily. So backtracking ends up being quite efficient. Here's my summary on backtracking algorithms. I've got my algorithm family summary of these two. So we talked about the other pairs as if they were solving the same problem. Brute force and greedy solved the same problem. Dynamic programming and D and Q solved similar problems. They solved the whole problem. But backtracking and branch and bound are different in the way that DP and D and Q were different, as in they solve different types of problems. So backtracking is one for constraint satisfaction problems. Usually any solution will work. We prune dead ends, any choices that break a constraint, and we get to a solution. Branch and bound is used for optimization. So we have to solve the constraint satisfaction problem, but we also want to do it in an optimal way. So we can prune dead ends and non-promising branches. Say, wait a minute, we didn't talk about branch and bound at all. We just talked about backtracking. I know. There's a whole lecture on branch and bound. It's a bit more complicated. But we did see that talking about constraint satisfaction problems and talking about optimization problems is vastly different. And so these two types of algorithms will be different. There will be a backtracking aspect of branch and bound built in, but there's also an optimization piece. And so we will talk about B&B as we come up. All right, there's my two pairs, and that leads me to the black slide, which is 2 minutes early for lunch. Let's get after it.